So if you're ranking ionization energies, what we're talking about is which one of these are going to be least likely to give up an electron or have an electron pulled away versus which ones are most likely to pull an electron away. So there's some factors we talked about. The most important one to consider is the noble gas configuration. But we said that only applies if that loss of one electron either makes or breaks a noble gas configuration. If it does neither, then you can't invoke that as an argument. And we talked about the next important one being shielding. And then we said maybe the fact that it has either a full or half full subshell. And then lastly, the number of protons. So there are a lot of things to consider here. So we'll start at the top. We'll look at each one of these elements and look at their situation. So for the K+, is the noble gas configuration significant here? Yes, if it's already a K+, it has the same number of electrons as argon. So if I want to remove one more electron from that, is that going to be easy or difficult? It's going to be very difficult. So this is going to have a high ionization energy, a high energy required to remove its electron. What about the Cl? Well, if it's a Cl neutral, it has 7 valence electrons, not the same as a noble gas. If I take one away and make 6, is that going to affect its noble gas configuration? No, it was not a noble gas configuration with 7. If I take one away and make 6, it still does not have a noble gas configuration. So either way, the noble gas is not a factor. So I can't use that to talk about the chlorine. And the same with antimony, Sb, it's number 51. It doesn't have a noble gas. It's not going to make a noble gas by taking one away. If I look at the Cl-, that has the same number as argon. So just like the K+, if I take one away, it's going to be very difficult to do that and break up the noble gas configuration it already has. So in that case, I'd say it has a high ionization energy. It's very difficult to remove one electron if it's got the same number as a noble gas. So now I would look at shielding. And shielding has to do with the number of layers of electrons. So for K+, how many layers of core electrons and where are the valence electrons? Well, normally potassium has 1 valence electron because it's in the 1s. But if it's a plus positive charge, it gave that away. So it lost its 4s electron. So K's outer electrons, well, its core are 1, n equals 1 and n equals 2. And its valence are n equals 3 because it lost its 4th energy level electron. For chlorine, same thing. 1 and 2 are the core, and 3 is the valence. For antimony, antimony is down a couple rows. It's down in row 5. So that means its outer electrons are in energy level 5. So it's 1, 2, 3, and 4 are its core. So antimony has a lot more shielding. Does that mean it's going to have a higher or lower ionization energy? It's going to be lower, because if it's got already a lot of electrons around the nucleus, that outer electron is going to be repelled by them. It's going to be much easier to knock it away. It's going to take less energy to overcome its attraction. So this is going to have a lower ionization energy. And the Cl- is also 1 and 2, core electrons, and 3 for the valence. So the shielding really only helps us to distinguish one of those 3 from the others. Looking at whether it's completely filled or half-filled subshells, the only one that really applies there is the antimony. We can see the antimony is element, it's the 3rd element in the P block. So it's the 3rd out of 6 columns. That means it's got 3 electrons in its 5p out of 6. So the 5p subshell is half full. Half full 5p subshell. So that makes it a little bit more stable. So that means it's not going to be quite as easy to take an electron out of there as we thought. But that's not the primary factor, right? That's factor number 3. So we look at the first 2 factors more. We're just trying to do a complete analysis. And then the next thing to look at is the number of protons. So K has 19 protons. Chlorine has 17 protons. Antimony has 51 protons. And chlorine has 17 protons. So now we need to kind of put this all together. If we look at the highest, well, maybe I'll start with the lowest on the left. The lowest ionization energy going to the highest ionization energy. So since the noble gas configuration is our primary factor, we're going to put the K plus and the Cl minus furthest to the right. It's going to be really hard to remove an electron from those two. Which of those two is going to be the most difficult to remove an electron from? Well, everything's pretty much the same except the number of protons. So since the K plus has 2 protons more than the Cl minus, those protons attract the electrons more. It's going to take more energy to overcome that attraction. So that should be the highest ionization energy of those 4. Then we can put the Cl minus, since it also has a noble gas configuration that we would have to break up in order to lose an electron. Then, between the Sb and the Cl, since the noble gas configuration was not able to be invoked for those, we would look to the next factor, which was the shielding. Since Sb has 4 layers of shielding and Cl really only has 2 core layers, there's going to be a lot more shielding in the antimony, so that one is going to have the lowest of the low. It's going to be almost no energy much at all to take an electron out of the antimony because that our electron's already repelled by so many other electrons due to the shielding. Right, so on the exam I would expect you to rank them and then to offer that explanation. To talk about the shielding, talk about the noble gas configuration where it actually applies, talk about the number of protons if it applies, and can help you make the difference. Questions about that? If we were looking at electron affinity, we would do a very similar analysis. Except electron affinity is a little bit different from ionization energy. It means you're adding an electron rather than taking one away. So we'd still consider the same factors in the same order, but we would look at them from the perspective of adding electron. How much does the atom want to add a new electron in versus take one out? So if we have the K plus, which has a noble gas configuration, and we're going to make it add another electron, is it going to attract that electron strongly or not? No, because it already has a noble gas configuration. It already has a correct number. So this is going to have a low electron affinity. Electron affinity is the ability to attract new electrons. It has a very weak ability to attract a new electron. Looking at the Cl, the neutral Cl is going to have a very high electron affinity, right? We did a whole lab about this because the Cl is one away from a noble gas. Adding one electron will make the same number as a noble gas. That will be great. So it's going to be very attractive for that extra electron. The Sb, yes, it will be closer to a noble gas by adding one, but that's not helpful. If we're talking about electron affinity, we either have to make or break the exact number of electrons as a noble gas by adding one more if it's going to be a factor. And so since the antimony neither has a noble gas configuration, nor will make one by adding one electron, it's not a factor. We can't invoke that to explain it. But the Cl minus does have a noble gas configuration, so it's going to have a low electron affinity. It's not going to attract another electron well if it already has a stable number. So that allows us to already rank the chlorine as the highest because the noble gas configuration is usually the biggest factor. And it's the only one that can make a noble gas by picking up one electron, so it should pick up that electron very strongly. And we could probably say that the Sb might be next because the noble gas configuration is not a factor there. But for the Cl minus and the K plus, those do not want to pick up another electron. They already have a stable number, so they might have the lowest electron affinity. Between them, The only major difference is the number of protons. So since the K plus has more protons than the Cl minus, it's going to attract a new electron a little bit better with that extra positive charge. So we would say it's going to have a slightly higher electron affinity than the Cl minus. So on the exam, for questions like this, I think maybe it's like a 6-point question. Only 2 of the 6 points are actually for ordering them correctly. So like 2/3 of the points come from the explanation that you give, and it should be thorough, and it should invoke all of these whenever they are necessary or significant. Any questions about that? Also make sure that you can rank sizes. So if you're ranking the size, it's a little bit easier. Really for size, we only have to worry about shielding and the number of protons. So that would be much easier to do. And for a question like that, you would need to explain it just like the other ones. But in this case, shielding is the top factor. So the SB is going to be the largest. It's going to have the largest radius because it has so much more shielding pushing the outer electrons away. Between the K plus, the Cl, and the Cl minus, they have basically the same amount of shielding. Very similar numbers of core electrons. Same number of core electrons, similar number of valence electrons. So the difference there is going to be the number of protons. So with the extra protons in the K plus, it's going to be the smallest. Well, but then the Cl minus and the Cl have the same number of protons. So we have to go back to shielding again. Even though they have very similar amounts of shielding, since they have the exact same number of protons, if there's a slight difference in shielding, that's going to make the difference. So since the Cl minus does have 1 negative charge more than the Cl, that extra negative is going to cause more repulsion with the negatives that are already there. So it's going to be slightly larger than the neutral chlorine. So if you use those factors, you should get a reasonable ranking. There are other subtleties that I don't expect you to know, so if you get your ranking based on those factors, even if it's not totally correct, I'll still give you full credit for it, because the idea here is that you can use these factors and talk about how they affect the sizes and ability for atoms to gain or lose electrons in a reasonable way.